if you see at the tuning, you see there is a range of parameters you can have. So for example, integral time constant goes from 0.01 to 1,000. If I could take tau I all the way to infinity, then I would have pure peak control, no integral action. And probably at 1,000 is going to be pretty close to no integral action, so you probably can use PI with tuning for tau I, the maximum by 1,000. However, the mode control allows you, with some wiring, to have true proportional action. Let's assume that F is simply grounded, 0. I'll tell you what, I'll go switching back and forth between the two, okay, because I still think. Let me just go back. All right. So I'll go between the two. You can see. So for the moment, assume that F is grounding, so F is 0. Okay? Or nothing connected with it. And let's follow what happens if I have tau d, that's the tau d of derivative action, that's pretty much the tau d of the conventional controller. Okay? Let's assume tau d equals 0 and F is not connected. And let's assume that we have selected, so we have the standard notation, so this side takes the plus, this side takes the minus. Let's follow what's the output of this device. So what do we have in this case? So let me write it down. So what we have now is tau d equals 0, F not connected to ground. So let's look at the picture. We have two signals coming in. And so this signal comes here, breaks into two, goes directly to this plus, comes here, but tau d is 0. Because tau d is 0, what comes out of here? 0. So this is y prime bar plus 0. I have y prime bar coming here. Everybody sees that? On this side, what I have? Y prime bar set point. If it's plus and minus, what's the result coming here?
0.
The error, right? Set point minus measure. 1. Where did you lose? Tau d is 0, right? I tune tau d to be 0. So this signal here, since this if tau d is 0, this transfer function is 0.
Yeah.
So 0 gets added here. Feeds the y prime bar. So y prime bar comes here. You add 0, so it's still y prime bar here. This is set point. Comes here, so it's set point that. If it's this choice that we made, it's set point minus y prime bar.
Yeah.
So that's the error. So the error comes to this box. BG proportional gain is the indetermination terminology for KC, the controller gain.
Did you say ammunition?
I said termination, so that's terminology. Okay. The indetermination terminology. Okay, so the indeterminology for KC. So that GE that you see here is going to be, so that GE is going to be Kc times y prime bar set point minus y prime bar. In other words, Kc times E bar. So it takes Kc times E bar, that's the GE. F is 0. If 0 is the input transfer function, what's the output here? 0. So Kc bar plus 0, that's what comes out. Okay? That R that you see here, since F equals 0, R equals 0, U prime bar equals Kc E bar plus 0. Oh, no, that's not right. Okay? So, here's the sum of Kc bar. This is 0, R is 0. Kc bar plus 0, the result is Kc bar. Pure proportional action. Okay? So that's how you set the mode control if you just want proportional control. Now, here's the nice trick. To get integral action, what you have to do is, you have to connect with the wire the screw that is for F with the screw that is for U prime bar, for the output. They are located. So you need to connect this controller output with F. So you need to run a wire between 14 and F. If you connect the two things with the wire together, then you make them the same. With me? Making question? Andrea, okay? So if I'm going to connect now with the wire, the F and the U prime bar, in other words, and it says here output because that's the controller output. You understand? That's not the measured output, that's the controller output, that's the U prime bar, what leaves the controller, okay? So, we're going to connect the two with the wire together, which makes F now equal to U prime bar. With me? So let's see what happens. So now, tau d equals 0. F connected to output. That was U prime bar. Nothing changes. Tau is still 0. Okay? So nothing changes in this part of the picture. G is not affected by that. F gets added here. So as before, G is going to still be Kc E bar. That's what we had before. But now things change. Now R, the signal that is coming back, okay, this signal here is 1 over tau I s plus 1 times the F signal. In other words, 1 over tau I s plus 1 U prime bar. Because F is equal to U prime. So now what leaves this summing junction, which is the output, U prime bar, is going to be G plus R, which is G is Kc bar, and R is 1 over tau I plus 1 u prime bar. With me? Answer okay? So, I have u prime bar both on the left hand side but also on the right hand side. Let's see what is the net result of this. So moving the u prime bar to the same side, I have u prime bar minus 1 over tau I s plus 1 u prime bar equals kc e bar. Make u prime bar common factor. So you have 1 minus 1 over tau I s plus 1 u prime bar equals kc e bar. Common denominator, tau I s plus 1 minus 1 over tau I s plus 1 u prime bar equals kc e bar. The plus 1 and the minus 1 cancel out. Okay? What happened to my work? So those two cancel out. So, and you have tau I s over that, move that to the other side. So follows that u prime bar equals tau I s plus 1 over tau I s kc e bar, which can be rewritten as kc divided by tau I s 1 plus 1 over tau I s e bar. What's that? PI controller, a standard PI controller. So that's how the PI action is done. With that interesting wiring, if you wire PF, the controller output, you change it now to have PI. Sean?
I don't understand where E comes from.
E is the difference set point minus, okay, back here. Y prime bar, right? Tau d is 0. So this signal is y prime bar, here is also y prime bar, comes here, but tau d is 0, so that's 0.
Okay.
So y prime bar plus 0, y prime bar. See, y prime bar down here. Set point. And here we have selected, so this is plus, and this is minus. So what do I have here? Y prime bar set point minus y prime bar, what's that? E bar.
Oh. Okay.
This comes to this, multiplied by Kc. So G is Kc times E bar.
Oh. Okay.
Clear, everyone? Christian? Okay? So we had Kc E bar from here, 1 over tau is plus 1 times U prime bar when the two are connected, and the net result of the U prime bar is PI action. That was kind of neat to see how it's really done. Okay, now let's talk about derivative action. Now it gets a little bit harder. Actually, let's leave it. So now things will change because let's take now tau is different than 0. So the signal here is going to be y prime bar, and that will be whatever is in the box times y prime bar. So I'm adding y prime bar plus this guy. Okay? So that's what is coming. So what's coming to the summing junction? Tau is different than 0, F connected. So I'm talking about what is coming to this summing junction. What is coming out of here? This signal right here. Okay? Signal out of top summing junction. Is going to be y prime bar plus what's in the box, which is tau ds divided by, is that dg, tau d over dg right? So have your set point minus that. So what's going to the PG box?
What does that say? Tau d over
D sub g.
d sub g.
Here, if you can see here, there's a dg here. I wrote this D sub g. So, what comes to the PG box is the difference between the set point, I'm talking about this signal here, coming to the PG box, is this, which is set point, minus what was coming before. So it's going to be set point minus and let me rewrite that. Set point minus y prime bar is 0, so I can rewrite that as E bar minus tau d s over tau d over dg s plus 1 y prime. So GE, which is what comes out of the gain box right here, so that means that GE is going to be Kc times this. Okay? So that's what the GE signal is. Now, here is the tricky part. We have just y prime bar, we don't have E bar. So that is not equivalent to some that the controller will have. So for example, if F was unconnected, I would have Kc bar minus Kc this. The controller was not connected, I should be getting PD the controller. So what is playing the role of PD controller? Often, usually for process situations, the set point is changed as piecewise constant. If the set point is changed as piecewise constant, derivative action is tau